dynamical uh, variables. Uh, for a system of for a system of arbitrary uh, number of uh, number of particles has to be constructed. अब इसमें यू नो yesterday we had जो हमारे पास h था h we could write as ki ni sigma. So ki can be any additive one particle quantity. So ni is the number operator. We can write it in terms of ki ai dagger. तो अब हमारे पास ये है कि इट्स डिजायरेबल टू एक्सप्रेस एनी ऑपरेटर एच इन टर्म्स ऑफ आर्बिट्री सेट ऑफ क्रिएशन एंड एनिहिलेशन ऑपरेटर्स. तो वी आर गोइंग टू अप्लाई द सेम ट्रांसफॉर्मेशन जो हमारे पास थी. फॉर एग्जांपल द ट्रांसफॉर्मेशन जो ये हमारे पास है, सो वी आर गोइंग टू राइट फॉर एग्जांपल h जो है we can rewrite it as h can be written as, so we are going to write these creation and alienation operators को हमने for example कल हमने कहा था ai can be written in terms of bi and ai dagger can be written in terms of bi dagger via some we made some यूनिटरी ऑपरेटर और ऑपरेटर इनर प्रोडक्ट के साथ मल्टीप्लाई करके हाउ कैन रिलेट टू क्रिएशन ऑपरेटर्स और हाउ कैन रिलेट टू एनिहिलेशन ऑपरेटर्स. सो ए आई डैगर को इन टर्म्स ऑफ बी क्यू डैगर लिखेंगे, बी क्यू डैगर एंड बी आर एंड दे आर द इनर प्रोडक्ट स्टेट्स एल क्यू के एल आर. So this is inner product. So we can make transition from this to this via this Hamiltonian. Since since we know that, so यहाँ से यहाँ जाएंगे. Since we know that what I should say, L Q K I K I L R is basically these are two inner products. So ki inner product के one आएगा, L Q L R it will be so we'll keep it L Q K L R. So you can write it like this. अब if you remember, अगर आपने पढ़ा होगा, if you had studied inertia tensor, आपने पढ़ा है ना inertia tensor, how we can represent it, how we can represent all components in an inertia tensor, जैसे A00, A11, A22, all the quantities, how we can express them. So you can express the same thing here also. You want to express, for example, H एज हैमिल्टोनियन जो हमारे पास है, इसमें काइनेटिक भी एनर्जी भी हो सकती है या इसमें म्यूचुअल पोटेंशियल एनर्जी भी हो सकती है. सो फॉर एनी स्टेट, फॉर एग्जांपल एनी पोटेंशियल V, वी कैन राइट इट एज 1/2 सिग्मा I इज इक्वल टू 1 Ni Nj Vij. So Vij can be all, जिस तरह हमारे पास inertia tensor में है ना, they can be all components you can have. So in the same way you can have all the components and for these two particles Ni Nij and जो इनके components along different directions हैं. So if you इसको अगर tensorily if you want to open it up, it will be basically एक तो ये होगा. So these are simple components or and plus Ni minus 1 into V I. So these may be off diagonal components and these can be the diagonal components. So you can write them these things in a compressed language को हम ऐसे लिख सकते हैं. If you remember in your earlier classes, in your how we study inertia tensor, we can write this tensor को हम ऐसे भी लिख सकते हैं. Both डायगोनल एज वेल एज नॉन डायगोनल कंपोनेंट्स को हम ऐसे भी लिख सकते हैं, एन आई एन जी माइनस एन आई डेल्टा आई जी वी आई जी। सो इसी को विदाउट लॉस ऑफ जनरलिटी नंबर्स वी आई जे फॉर्म है सिमेट्रिक मैट्रिक्स। अब ये हमारे पास एक, अगर हम इसको इन टर्म्स ऑफ पेयर डिस्ट्रीब्यूशन ऑफ द ऑपरेटर, पेयर डिस्ट्रीब्यूशन ऑफ द ऑपरेटर, देन इसका फॉर्म जो हमारे पास आएगा, द फॉर्म विल बी लाइक दिस, इसका इस इक्वेशन को फॉर्म जो हमारे पास आएगा, इट विल बी ऑफ दिस काइंड। इसका फॉर्म आएगा हमारे पास पी आई जी will be NING, it will be NING minus delta IG NI। आप देखो यहाँ पर जो n है ना हमारे पास, कल n को हमने इन टर्म्स ऑफ ए डैगर लिखा था, बोथ एज क्रिएशन एंड एनिलेशन ऑपरेटर आएगा। तो हमारे पास NING है, सो ए डैगर आएगा, फिर ए डैगर आएगा। सो दिस होल टर्म कैन बी सीन इन टर्म्स ऑफ ए daggers, such that if we want to open it, we can say 1/2, it will be bit of algebra ij, it will be basically BQI dagger, BQI, या फिलहाल हम BQ पे नहीं आएंगे, विल राइट इन टर्म्स ऑफ द AI dagger, AJ dagger, AJ, AI and VIG. So what we have done is we have written this, जो हमारे पास ये sort of inertia tensor, जिस तरह हमारे पास ये जो quantity है इसकी both components of diagonal this and both components of diagonal and diagonal components मिला के ये वाली quantity हमारे पास आई। Since n को हमने in terms of creation and annihilation operators लिखा था, यहाँ NING है, so we'll have two creation and two annihilation operators in this thing multiplied by this VIJ. These are the components we are having. अब इसी चीज को हम, if we want to, again we are going to see AI in terms of for example AI dagger को हम ऐसे लिखेंगे in terms of BQ dagger LQKI. In the same way AI can be written as sigma Q KI LQ BQ. So we have written AI in terms of BQ, AI dagger in terms of BQ dagger. Again we are going to just substitute them here. जो हमारे पास V का फॉर्म आएगा, it will be 1/2 sigma BQRS. So it will be BQ dagger BR dagger BS BT QR VTS. Yes. और IJ हमारे पास आएगा, IJ will take this form LQ QI KI L और KJ LS VIG. आप देखो इसमें I am not able to write it properly. You will see here for example LQ KI and KI. So ये inner product है KI ये ऐसे आएगा KI it will be 1 basically sort of thing. इस तरह KJ it will also be 1. So at the end if you see like this LR KJ LS VIG. So हमने ये इनको creation and annihilation operators को once we made this we wrote creation operator in terms of BQ dagger, annihilation operator in terms of this BQ via some inner product. इसको हमने यहाँ पर substitute किया, and some of the things जो इसमें है norm जो inner product of the same thing KI it will be 1, and at the end it will simplify as QR VS TS. अब देखो ये हमारे पास दिस इज एन ऑपरेटर, दिस इज ऑल्सो स्टेट एंड दिस इज ऑल्सो स्टेट. जो हमारे पास स्टेट है QR, यहाँ पर स्टेट है, यहाँ TS स्टेट है. तो यहाँ मैट्रिसेस ऑफ दो ये है ना, एक normally operator state and state can be written as an matrices, it can also be written matrices. अब ये matrices हमारे पास आएगी in the form of two particle operator matrix elements, two particle operator matrix elements आएंगे. And in that sense we can write it as QR V S of t. You can write it like this. So this is a simple expression हमने कैसे किया कि how we can write dynamical variables in terms of जो number operators की definition लेकर and creation and annihilation operators को relate करते हुए how we can relate them. And at the end we got what I should say, we got a two particle operator matrix elements which are given by this equation. अब हमारे पास another exercises, for example, the thing is I have been repeatedly saying that we are doing this what I should say, we are doing this one continuous one particle spectrum and continuous one particle spectrum continuous one particle spectrum and quantum field operators. So अभी तक हम जो कर रहे हैं ना, in the sense we are relating one particle operators या one particle states जो हमारे पास हैं. तो we are they can have both discrete eigenvalues or they can have continuous eigenvalues. तो हमने कहा था पिछली बार भी, when an operator acts on a state it gives an eigenvalue. अब acting on a state giving an eigenvalue, that may be a continuous thing or the eigenvalues may be continuous, they may be lying on a range of values, continuous range of values. तो हमारे पास integral आएगा. Or the eigenvalues may be discrete. The eigen may be. So if you want to have a normalized state, हमारे पास एक state है, for example, one particle basis which belongs to complete continuous spectrum of complete set of commuting operators symbolized by x. Then one particle eigenvectors which can be normalized, they can be written like this. They can be written like this: x prime sigma prime x double prime sigma double prime. So you can see it. तो आप यहाँ पर देखो, आप यहाँ पर you can have both this Kronecker delta हमारे पास आएगा, sigma and sigma double prime are related, sigma and sigma double prime are related. So you can have a sort of Kronecker delta for this. It may, the value may come out to be 1 or it may somehow not. So in the same way, what we can say that continuous eigenvalues x prime of x and discrete. So we can have x and x prime, they take as continuous eigenvalues, and sigma prime you can take it as discrete what I should say eigenvalues which are represented by these basis vectors here. And discrete sigma may be represented by z component, for example spin of the particle. तो अब ये जो हमारे yesterday's what we did is basically we had an how we arrived at Bose-Einstein statistics and Fermi-Dirac statistics by particular जो हमने commutation relations, how we arrived at the commutation relations. So in the same way what we are going to see जो हमारे पास ये whether for discrete eigenvalues or whether for continuous eigenvalues, how we can rewrite the Bose-Einstein and Fermi-Dirac relations. For example, Bose-Einstein में है ना ऐसे A dagger, AL dagger minus AL dagger, AK dagger is equal to 0. फिर आएगा so on and so forth. It will be AK AL minus AL AK is equal to 0. AK AL dagger minus AL dagger AK is equal to delta KL I. In the same way, we have Fermi-Dirac statistics. Fermi-Dirac statistics में सिर्फ ये है कि यहाँ माइनस नहीं आएगा, यहाँ प्लस आएगा. यहाँ माइनस नहीं आएगा, प्लस आएगा, प्लस आएगा. So we'll have both commutators and anti-commutators in that sense. For Fermi-Dirac case, we have anti-commutators. For Bose-Einstein, we have commutators. तो अब in the same sense जो अब हमारे पास if you want to write this discrete and continuous eigenstates, so how we can write them? So for Bose-Einstein case, we can have psi A जो commutation relation है, you can write it in terms of continuous and discrete things like this. Psi sigma r prime 0. Psi A r prime, psi A dagger r double prime minus psi sigma double prime, psi sigma dagger prime r prime is 0. तो ये एक आएगा. And the other relation ये तो है ही है. But the thing is for discrete and continuous, so you are going to invoke this very property. You can see it like this. You can see it like this. Psi of A r prime, psi of sigma dagger r double prime minus psi of sigma dagger r double prime psi of sigma r prime is equal to जो हमारे पास ये delta function है, which will take into consideration both continuous eigenstates as well as what I should say discrete eigenvalues. Both they will take. Now in the same way we can go for Fermi-Dirac. Fermi-Dirac में सिर्फ ये एक आएगा. Now you have minus here, minus here, minus here. Now we can have plus. So we will have plus. We'll have plus. So and the same thing is there. We can write it in that sense. अब इसमें सिर्फ एक चीज है हमारे पास, the operator represents the density operator, the density at a position r prime of particles for which discrete variables have the value. तो number operator हमारे पास जो होगा number operator.
Sir, es kaitas ein value asan possible as.
Huh?
Ye kaitas ein state chase divan the equation.
Time state मतलब
At kaita ein values asan
नहीं,
possible.
अब
For
अगर
example,
discrete eigenvalues, अगर we are taking discrete as well as continuous eigenvalues, so we are representing an equation which will take into consideration both. अब जो discrete eigenvalues अगर आसन, they will be periodically they will be discrete. If it's continuous, it can have a range of values. Depends कि operator की state जब act करेगा, so it can have continuous spectrum of values. So the point is कि how we can represent जो हमारे पास जो commutation or anti-commutation relations, yesterday we did it for Bose and Fermi statistics, which represent symmetrization of wave function and anti-symmetrization of wave, those type of particles के लिए. But yesterday we did not, we are not conscious of the fact whether the eigenvalues or eigenstates are discrete or continuous. In today's thing is, in this notation, we just incorporated both continuous eigenvalues as well as a for notation also in the first place. And taking the definition of number operator n, which is basically equivalent to A dagger A. ठीक है? Continuous can take any sort of values. Discrete will take only some values, specific values, discrete, quantized values जो भी है. So we are formalizing this equation, जो इसकी last तीसरी वाली equation है, it will have both this discrete as well as continuous eigenvalues. So this is what we are.
Mera confusion akhas sir.
हाँ फरमाएं।
Sir, is continuous eigenvalue carry can't value pick up.
Continuous means any continue between it can take any value. Yes,
मगर
yes.
अगर इस discrete करो count इस कौन discrete ते infinite count करें, for example 0
No,
1
no,
2 3
discrete
up
in
to
the sense
infinity.
that it will take, for example, it will take values multiple of some discrete value. For example, 3, 6, 9, 12 ऐसे आएगा. It will not 4, 8, 12 like this. It will come. It will come multiple of some discrete value, a particular quantity, which is discrete.
Yes sir.
जो हमारी जो बेस स्पेस है ना, फॉक्स स्पेस जो हम कंस्ट्रक्ट करेंगे फॉर वन पार्टिकल स्टेट, सो इट कैन बी डिस्क्रीट स्पेस, सब स्पेस, और इट कैन बी कंटिन्यूअस सब स्पेस. So in discrete subspace, which is basically that, which is part of that Fock space, out of which these one particle states are constructed, that discrete space is basically you can have only discrete eigenvalues, uh, multiple of some quantity. That may be infinite. That's not the problem. Those discrete values, उसकी जो series भी infinite हो सकती है. But the thing is that it will have it will take values in only in those discrete multiples. While in case of continuous eigenvalues, it can take any value. You got my point? Our discrete series भी infinite हो सकती है. That's not our case. It's not the point. Point is, it will take discrete, can take discrete values as well as continuous values. So discrete and continuous eigenvalues के लिए ये हमारे पास जो third equation है ना, delta r minus r prime, we can represent it by this. This is our point. How we can represent. So हमारे पास जो symmetrization of and anti-symmetrization of wave function है psi and in terms of Bose-Einstein and Fermi-Dirac, how we can represent, how we can incorporate those very things in this case also. This is our point. ठीक है? You got my point? Oh, hello?
Yes sir.
Okay.
Yes sir. Yes sir.
Okay. So this is what we are doing. So in the sense, so this is simply we are just trying to see it that basically हमारे पास जो ये है ना, ये infinite dimensional space. So जो हमारे पास quantum field theory वो जब हमने कहा ना कि psi is equal to n1, n2, n3. So one particle states, two particle states, n particle states. हमने लिया n1. N1 means particles of the same kind. Yeah. फिर it later it may be a Bose particle or a Fermi particle, बाद की बात है. So you can take in principle any. So उस one particle state को हम define किया Fock space पे. That's an infinite dimensional space जिसमें different states होते हैं. उन्हीं states पे vector spaces पे और states पे operators are acting on these one particle states. The operators may be creation operators, they may be annihilation operators. उसका algebra हमने previous class में किया, and it's the continuation how we can represent that algebra. That algebra can be represented like that for bosons as well as for fermions. And अब हमारे पास number होगा number operator n, for example, so psi a r and psi a prime r represent the density at the position of particles for which the discrete variables has a variable sigma. Then n can be represented as sigma dagger r, है ना, and sigma dagger r prime. If it's a three-dimensional space, तो हम उसको ऐसे भी represent कर सकते हैं. And for an additive one particle states, जो हमने अभी इससे पहले किया था, h को हम कैसे represent करेंगे for this thing. So we can represent it like so integral जब आएगा तो you can have a range of values. So h जो अभी हमने इससे पहले किया था, h can be represented as sigma prime. So psi sigma dagger r prime. So you can have this sigma prime. This is k. This is r prime sigma double prime psi sigma double prime r for 3 dimensions. So अब ये हमारे पास ये continuous eigen states भी है और discrete eigen states को हम ऐसे represent कर सकते हैं इसका Hamiltonian. And so अगर हम ये तो one particle state है, one particle. वन पार्टिकल में हमारे पास दो मैट्रिसेस निकाला हमारे पास टू फॉर कंटिन्यूस एंड डिस्क्रीट के लिए हमारे पास ये आएगा ये तो ऑपरेटर है दिस इज टू पार्टिकल ये हमारे पास आ गया बेसिकली टू पार्टिकल मैट्रिक्स हमारे पास आया तो अब So we can have this, for example, this is two particle state. So इसके ये आएगा. Now you can have जो इसका two particle state का भी आएगा. If you have, for example, two particle operator. So इसमें it will come in the form of sigma drag. So इसका जो V आएगा ना ऐसे, it will be like this 1/2 sigma prime. वन पार्टिकल के लिए आएगा दो मैट्रिसेस टू पार्टिकल के लिए आएगा ये चार आएगा सो यू कैन हैव इंटीग्रल लाइक दिस सो यू कैन अकॉर्डिंगली डू इट फॉर सिग्मा आएगा सिग्मा सी डैगर और डबल डैट सिग्मा so you can continuously you are going to increase it that way in that sense so maybe so we'll stop here. We are going to continue with this algebra from tomorrow and see very important property हमारे पास है formula उसका हम थोड़ा सा कल will see its derivation how we can derive the same thing in that Fock space. So in today's class what we did we simply जो हमारे पास commutation and anti-commutation property है for Fermi-Dirac and Dirac Bose statistics उसको in terms of number operators and in terms of continuous and discrete eigenvalues को हम symbolically how we can represent them. So this was our aim today's class. So we'll stop and we'll continue tomorrow.
Thank you, sir.
Okay.